Giving it a couple of minutes, I think it's maybe time to start. Can you all hear me okay? Well, thank you first of all for getting up bright and early this morning. It may not have a big audience, but hopefully we've got an audience be interested to hear what we've got to say here. So I think the key thrust of our talk today is putting the phrase high availability and disaggregation into the same sentence. You hear a lot about high availability, you hear a lot about disaggregation. What we'd like to do today, maybe wait for a few more people to come in, is bring those two themes together. Morning. So for those of you aside from Mark that don't know me, my name is Pat Moore. I'm responsible for sales of our networking technologies in Europe. So I think many of you will know of Metaswitch. We've been around for 30 years. But for those of you that don't, let me just give you a very quick thumbnail. The core of what we do is to develop protocol stacks. So layer 2, layer 3, MPLS, OEM, whatever else comes along. And we develop that source code and we license that source code. Now, traditionally, those customers have been the hardware equipment manufacturers, and you can see some of them up there. And you'll find our protocol stacks embedded in a huge number of devices, both in the data center and in the telco and service provider space. There are examples of both up there in our customers, but actually if you look over the full breadth, we've got a lot more experience in the telco space than we have in the data center. And I think in part that's because that's a more interesting and more complicated networking problem to solve. The data center is perhaps a little bit more straightforward. So what are we doing here at OCP? Well, increasingly, people are looking at deploying white boxes as alternatives to expensive, traditional, branded equipment. And to that end, we have first of all worked within the OCP to help some of the standardizations process, particularly in the area of the switch abstraction interface. That's the interface between the protocols and the white box switches. And we've developed an architecture to facilitate our customers taking our source code and very quickly assembling a complete NOS out of all the moving parts you need. And we've developed an architecture you can see on the left there, which we provide, and that's our NOS toolkit. So let's look a little bit more at disaggregation. We're obviously all very familiar with it in the compute space. It's been a massive success. And it's starting to show fruits in the networking space as well. Initially in data center networking, but also a lot of telcos, a lot of service providers are looking at what the data center networking guys are doing and saying, can't we get a piece of this action? Can't we get the ability to use the latest white box hardware that comes out very quickly, take a disaggregated software solution, bring it up on the latest hardware, drive down our costs and be more competitive in serving our customers. So what in particular I'd like to look at today is the subject of high availability. Now, everybody wants high availability. You want your traffic to continue flowing, whatever breaks, that's a given. In the data center, that's a relatively simple problem to solve. You can over-provision. You can make sure there are enough links, enough cross-connectivity. You can make sure there's enough excess capacity in all of your switches, all of your routers, all of your links, such that whatever fails, the data center carries on doing its job. The telcos and the service providers would also like to do that, but they don't have the luxury of being able to over-provision to that same degree. Traditionally, they've addressed the problem of high availability by buying expensive chassis-based systems from the equipment manufacturers. And what those chassis-based systems do is they have an internal modular architecture, and the idea is any one or any combination of those modules can fail, but there's enough redundancy within the whole chassis that the box continues to function, packets continue to be forwarded, the control plane continues to manage the device properly in the presence of other failures in the network. So let me now introduce Jonathan to you. What Jonathan is going to do is tell you some work we've been doing very recently with standard off-the-shelf white box switches and extensions to the architecture that we've developed here to allow high availability networking to run on these standard white box switches. Jonathan.
Thank you, Pat. So I'm Jonathan Cumming, and I'm a software architect and product development manager at Metaswitch Networks. And I'm really here talking because I've spent the last few years integrating our protocol software with various different customers' platforms, including in highly available scenarios and into sort of NOSes on white box switches. So let me start by talking about what I mean by a highly available router in this environment. Fundamentally, it's a single node in the network. So you're not making your network have more pieces. It's a single node from both the topology point of view, routing topology point of view, and from a management point of view. So for the operator, they've got a single device to operate. And it is tolerant to any individual failure. So any software or hardware component can fail, and the box will carry on working. That doesn't mean the failure doesn't cause any disruption, because obviously you could have a hardware failure that takes down some of your interfaces. But the main thing is that the router carries on functioning, and traffic continues to flow through the rest of the switch. And the key thing here is that the switch is operating in a way to minimize the disruption on the rest of the network. So if the switch died totally, then that might cause a topology change, which would cause disruption across the entire network. By keeping running, even with reduced capacity, you don't get that widespread disruption, and therefore you minimize your disruption of the network. Now obviously to do this, you need some level of hardware redundancy, so something can carry on working when one part fails. And for this project, or this demo, we've used a pair of white box switches, which we've stacked together to be a single data plane. So what does this mean to the software architecture that you need on top? So let me start by looking at these typical sort of NOS architecture. You've got some nice clear layered architecture with open, well-defined interface between each layer. At the top you've got the management, and the interface between the management and the control plane is then the Yang netconf type architecture. You've then got the router control plane, and then below that you've then got an open interface onto the hardware, onto a hardware abstraction layer. In this case you've got ONL and the SI APIs and so on to provide the abstraction from the hardware. This architecture means you can mix and match, you can run different applications on your switch, but equally you can swap out different components, run a different management system, run a different control plane, and move between different hardware platforms. Now, so to take this and run this on a stacked architecture, what we've done is to split the control plane in two. So you've got a control plane and a data plane component of what was the original control plane. And then we've added a distribution layer between the two to communicate between the two parts. Into the data plane part of it, we've then put in the function that is local to a single switch. It's the time-critical components. It's the components that are maintaining connectivity across individual links. And this allows us then to split, so one control plane can drive multiple data planes. So at the top, you've got the control plane, which is still your single router in the network, your single node, single management point. But underneath, you've then got multiple separate data planes, each running the function on that particular particular location. And then in the middle, we'll say that marked there as distributed fabric manager is providing the intelligence to determine what to program onto which switch. and to program the stacking link and so on accordingly, so the switches operate as a single data plane. So what happens if the data plane fails? Well, the control plane keeps functioning, keeps up its communication with its neighbors. What it sees is it's lost some of its interfaces. The neighbors in the network have also seen the set of interfaces go down and will route around that failure in the normal way. So the operator may have introduced lags or RSVP one-to-one protection or segment routing or whatever mechanism they have for providing a protected path. And this will trigger that behavior on both ends. Then, when the data plane comes back up again, it will reconnect the control plane. The control plane will reinitialize the data plane location, and once it's reprogrammed and replayed all the programming into that location, it can then re-enable those interfaces, and it operates again back as being a single redundant switch. So that's covered data plane failure, but clearly, obviously, the control plane could also fail. And for that, what we've done is we've added a backup control plane. So you've got the two switches, both of which have got their own CPUs, so you can run the active control plane one and the backup control plane on the other. So this backup control plane just sits there. It receives a replicated state from the active control plane. It receives a replicated configuration. And it's always there ready to take over if the primary one fails. And if it does fail, what happens? Well, the data plane carries on operating. The data plane is not affected by this, so it maintains its adjacencies, it maintains its forwarding of its time-critical packets, the LACP PDUs, the BFD packets, and so on. Meanwhile, the control plane starts activating up. Its replicated state, like the layer 2 state, so it can synchronize that with its neighbors, so you don't get any sort of traffic forwarding loops and so on. For the layer 3 protocols, the MPLS, VPN protocols, the standards bodies have defined grace or restart procedures, which allow the router to talk to its neighbors and relearn the routes they had earlier. So it goes through that process and it recovers its routes from its neighbors without causing any wider disruption. And then once that's complete, it can then check that the programming into the data plane is the same, or make any necessary changes to the data plane programming, and continue. All the while, the data plane continues forwarding. So you've got no network disruption, you've got non-stop forwarding of the system. Obviously, when the control plane comes back up again, the application restarts. It then just starts up as a backup. So it starts up again. It can become a backup again, so the system becomes again redundant and can deal with another failure. So that gives you the architecture that we've put together. But rather than just take my word for it, what I'm going to try and do, what I'm going to do to you is show you a recorded demo of this working. So the environment we've got is a sort of typical, simple telco type network. Each end you've got a customer site, and the provider is providing a layer 3 VPN service between those sites. So you've got two provider edge routers, which is taking the customer traffic, putting it through a VPN to the other side. Across the core network between the two provider edge routers, you've got another core router. So in the middle of the network, you're running OSPF as the routing protocol, LDP for label distribution, and then BGP for the VPN route distribution. At the edge, we've got OSPF running as the routing protocol. And then to provide the redundant links, we've got two interfaces into each of the adjacent nodes from the provider edge router 1, which one we're concentrating on here, which is a highly available node. You've got units 1 and 2 there. Those are the two individual stacked units. So on the left, you've got a pair of interfaces in a bundle. And on the right, you've got a pair of interfaces into the bundle. And obviously, each of the interfaces goes onto a different card, so the system can handle a failure of one of the units without breaking the connectivity across the network. I'm going to run a couple of different scenarios here. The first is to reboot the active control plane. So we're going to reboot the unit that's running the active control plane. That will trigger both the control plane failover to the backup, and will take out half of the data plane resources. Then we'll get that to restart and recover. And then we'll do a second one, we'll just kill off the control plane and see how the data plane carries on forwarding, but you'll still got to switch across to the backup control plane. So obviously to do this, you've got the both the handling of the fact you've lost these interfaces to the links and so on being reactivated or deactivated. But secondly, you've also got the graceful restart procedures going on. So if I just switch over. Yes, okay. Right, so in the top window, you've got basically the router CLI. It's also the window which will be actually running the commands to reboot and kill the software and restart the software. And that'll switch between two different windows. Obviously, in a real system, you'd have some remote API, some remote CLI, remote management, and you'd go in through some floating IP address into the active control plane. In this case, we've just got a PuTTY window straight into the two boxes, so we're switching between the two boxes to show you the CLI. But at any time, only one control plane is active. At the bottom, you will see there's a continuous ping going on between the two customer devices to prove that we've got connectivity across the network, and that will run throughout the demo. So let's go first of all for the first scenario. So to start with, did that work? Yes, start with all the control planes locations are active, and control plane on unit 2 is backup. Okay, you can see that all the interfaces here on the lags are up and running and being used. And to prove this is a router, those are the provider side routes, the ones across the core of the network. So now what we're going to do is just exit out of the CLI and reboot this unit. And all the while, you can see that the traffic is going end to end across the network. So when this is rebooting, what's happening is the other control plane is now activating. It is resynchronizing with its neighbors. It's relearning the routes across the network, and it's then auditing the data plane to make sure the programming is still correct. So if we now go on to the other CLI, and when we come into this, is now on unit 2, you can see we've only got 2 of the locations up. So the locations on unit 1 are both down. Only some of the interfaces are up. The other ones have gone away. But all the routes have been relearned. So we've replicated all the data across onto the backup. We've got a separate instance of the control plane now running, but it's still looking like a router. And the traffic's still flowing. We're now restarting the software on the first unit. It's been rebooted in the background, and we're restarting it. And now we can see it recovering. So initially, the control plane location on 1, which is the one we've just started up, is come up as backup, so it's running. But the data plane is still initializing, because it takes a while for the SDK and so on to come back up again. And then after a while, once the data plane's reinitialized, it goes into synchronizing state. And at this point, the control plane is now reprogramming it with all the current state, making sure it's all ready to go. And then when that completes, the data plane is now active again. So here we've got both data planes initialized and running. And if we look now at the state of the system, you've got all the interfaces are up, and there's all the routes are still there. So we're now back to a redundant system with two complete sets of control plane and data plane. This is now the second scenario. So we're now going to kill off just the control plane. And in this case, this is just going to cause the control plane restarts. So it's going to be the reloading of the routes and so on from its neighbors, but no data plane changes at all. So again, you've got non-stop forwarding, this time through all the interfaces. So if we now look at the state from on the new CLI, you can see the control plane, only one of them's up, but both data planes are still running, and all the interfaces are up, and all the routes are still up. And it's still forwarding. Okay. So, I mean, hopefully it's a bit quick, a bit rushed through, but that's obviously a recording. If you want to see a real demo, a live demo of it, then obviously we can arrange that, and we can do that with you remotely over the phone and so on, using a shared sort of remote desktop type session. So that's very straightforward to set up. But hopefully what I've shown really is that by taking standard hardware, there's nothing special in this hardware. We've got some clevers in the software, and by splitting up the function carefully and adding that sort of that intelligent layer to distribute the function between the two line cards, we've created a highly available system out of straightforward, off-the-shelf white boxes. So I want to pass you back over to you, Bat.
Thank you, Jonathan. Yeah, I hope you all enjoyed that presentation. I hope that gave you some ideas. So just a few closing words from me. This is a resource we've got available on our website. There's a link down at the bottom there. This is a NOS cookbook. So this is quite a detailed document that is a guide to how to build a portable NOS for telco type applications running on standard white box switches. It obviously includes a range of OCP technologies. Those are obviously very useful tools to help build all of this. And the key thrust of this architecture we put together is, here's an architecture. This architecture will run on any white box system for any kind of application. And another key part of, I think, why people want to move to more modern disaggregated systems is to get improved operational costs for these devices. So included in this architecture are modern and open interfaces that are amenable to automation. And that, again, as I say, is one of the key savings. So please take a look at this NOS cookbook, and hopefully that will seed some ideas in your mind as to how this can be moved forwards. In addition to the NOS cookbook, we also provide our NOS toolkit. That's a very specific product. That's a set of source code out of which you can build this. And our thinking here is that for this disaggregated market to take off, there needs to be an ecosystem of NOSes out there. There's probably no one NOS that fits all applications, data center, telco, service providers. There's PON access applications, there's disaggregated cell site gateways, there's a myriad of different applications. So our approach to solving that is to provide a NOS toolkit and to facilitate our customers to build a variant of a NOS that is targeted at a particular market application, and to help seed an ecosystem of solutions out there. Some may be open source, some may be closed source, but to give customers a choice here to build a NOS that facilitates all of this happening. And of course, essential to all of this is some of the OCP technology. The SAI is the one perhaps dearest to our hearts. That's the one that's closest to us, so there's a link up there for that as well. So I think we'll stop there. If, as Jonathan said, you want to see more, please come and talk to us. Otherwise, please, any questions? Thank you.
So what type of protocol is running between control plane and data plane?
You can probably handle that one better. Jonathan?
What, between the two control plane data plane locations?
No, he said between control and data plane.
It's just passing messages. So it's
So it's gRPC or?
No, we're not. You could map to that. We actually no. It's just running. It's proprietary in that sense. It's the messages between the control plane components, because our software architecture has got the ability to put modules wherever you like in a distributed system, and we've used that, and we're just piping over a TCP connection between the locations. We have customers who have mapped that onto things like gRPC, so it's possible to do. But for this, we're just putting it through a TCP tunnel.
So what kind of NOS did you use? Is it Metaswitch NOS? It's your proprietary.
This is done with our NOS toolkit.
This is
correct. Yes.
It's not open source.
Sorry.
It's not open sourced.
This is not. This is our our control plane software is not open sourced. Correct.
Yeah, I mean, we built it on top of ONL, so yeah, parts of it are open source, but the protocol stacks, the distribution layer that Jonathan has described here, that's a closed source solution for this particular.
Also for MPLS, everything. Also it's
Yeah, the protocols are all closed source. Clearly, the architecture is applicable to any. Not any control plane, but it uses our control plane, which is closed source. Yes.
Do we handle partial control failure?
Okay. You can do that. That's another level of complexity. You can, because we have a modular architecture for the individual control plane components, you can compartmentalize those. So you can run a separate set of components, for example, per VRF, in a separate OS task. And then you can, if that particular OS process dies, you can restart an individual VRF. So there's a way of compartmentalizing it further if you want to handle more granular failures. This does not. The demo I showed you doesn't go to that level of detail, but certainly we've got customers who, they run each of their VRFs in a different Linux process, which means that they can all fail individually without killing the entire box.
Yeah.
How is the solution related to SDN solution?
How is it related to SDN?
SDN.
Okay. There are many meanings of SDN. If I take the meaning of SDN being some centralized brain that knows about the state of the network and is then controlling the individual routers, then if you look at this, you could take the management component at the top and put that remotely on your SDN controller. So that would know what to program, and then it's sending instructions down into the control plane to actually then program the SDN, the routes.
It's software defined in the sense that a central controller might be using something like netconf to provision the routers. It's not SDN in the sense that all of the control plane is running in a central PC somewhere and the data plane is just handling dumb operations. We particularly some of the high-speed operations like BFD and LACP, where you need to recover very quickly, you have to have those protocols actually running adjacent to the switch. It's the only way you can do fast reroute around failures.
We also do support PCE, if you happen to use PCE as the mechanism for SDN.
Yeah, PCE protocol, yeah.
PCE protocol.
Another question.
Yeah.
What's the SAI version I currently support?
I don't know.
Don't know the answer to that, sorry.
Okay, clarify. You can't do this, all of this on SAI. So we've had to go straight to the Broadcom SDK for this because the SAI isn't rich enough to do all the function we need to do. We've got a SAI integration, but we didn't use that for this because it's another layer of complexity. It'd be great if we could use SAI directly for this, but say there's another chunk of work to do that.
I mean, if this is technology that's of real interest to the market, then that's obviously some work that needs to be done. It's definitely.
So you always saw SAI somewhere on the slide.
Yeah, we've got SAI integration, so yes, you can use SAI, but we have this particular demo wasn't using SAI because of it didn't fit the project.
And that sort of alludes to what I said earlier, that there are quite a number of different ways of building a NOS to this architecture using slight different variations, and one way of doing it is to go straight to the SDK, another way of doing it is to go to SAI, and there are other ways you can do that same connecting as well. Yep. Okay, thank you.
Thank you very much.